everyone, welcome to my YouTube channel. Today I'm solving Leetcode question, redundant connection. This is also very classic graph problem. In this problem, a tree is an undirected graph that is connected and has no cycles. So this problem defines a tree, and then in this definition, a tree means undirected graph, and then it's connected and has no cycles. So undirected graph means, like, say, in the graph the edges are not directed. It's not like, say, if so the edges 1 to 2 in this example, edges 1 to 2 is the same as the edges 2 to 1. So there's no direction. If this graph is directed, then the edge 1 to 2 is different than the edge from 2 to 1. So here, this graph is undirected. So 1, 2 just indicates, okay, there is an edge between 1 and 2. There is no directions. Let's say which node points to which node. It has no cycles. So no cycle, what does the cycle mean? So for this example, this forms a cycle because starting from node 1, you can go to node 2 because there is edge connected to 2. From node 2 you can go to node 3 because there is edge. From node 3 you can go to node 1 because there is an edge connecting node 3 and node 1. In that case, you're starting from node 1 and you return to node 1. In that case, you form a cycle. So this does not satisfy the definition of the tree. So you are given a graph that starts as a tree with n nodes labeled from 1 to n, with one additional edge added. The added edge has two different vertices chosen from 1 to n, and there was not an edge that already exists. The graph is represented as array edges of length n, where edge 1i equals ai bi indicates there is an edge between node ai and bi in the graph. Return an edge that can be removed so that the resulting graph is a tree of n nodes. If there are multiple answers, return the answers that occur last in the input. So basically, this is like initially you have a tree with an node, so that satisfies our condition. And then we add one additional edges. So in that case, we add an edge. So in that case, we create a cycle. So it does not satisfy the condition for a tree. So remember, there's only one additional edges. So in that case, we want to remove these additional edges so that in that case, we can create a graph of the tree, which means undirected graph, connected, and no cycles. Here it asks to return the answer that occur last in the input, but here essentially we just add one additional edges. So we just remove one redundant edge. That's sufficient. We only need to remove one edge. For example 1, so the edges are given 1, 2, 1, 3, 2, 3. So in this case, to remove the cycle, we remove the edge of 2, 3 because it occurs the last in this edges list. After we remove it, there is no cycle. In the example 2, the edge given is 1, 2, 2, 3, 3, 4, 1, 4, 1, 5. In this case, the output should be 1, 4. So remember there is a cycle between 1, 2, 3, 4. And then since this 1, 4 occurred last in this edges list, so that's why we remove this edge. So after we remove the edge 1, 4, there is no cycle. So it satisfies the definition for the tree in this problem, which means the tree is undirected graph that is connected and has no cycles. So there are two ways for solving this problem. So the first method is unifying. So basically by unifying is, okay, so given this list of edges, so if they are connected, then they form a set. They are in the same subset. Then we can union these two. So let's say in this case the edge 1, 2 are connected, so we can union those two. And then edge 1, 3 are connected as well, so we can union 1 and 3. And now we have additional edges 2, 3. So we find the parent for 2 and then the parent for 3. And then we realize that, okay, if we want to union 2, 3, before we can union it, since we already have edge 1, 2 and edge 1, 3. So the edge 1, 2 and 2, 3 are already in the same subset. So in that case, we do not need to perform the union operation with the given edges 2, 3, because after checking the parent for node 2 and parent for node 3, we realize that they are already in the same subset. So we do not need to perform the union for these two. So in this case, we find the redundant edge, that is 2, 3. Using union find, so remember, the redundant edges to be output is always the last occur edges in the input. Because previously, let's say, when you are checking before you reach the node 2, 3, you still can union or merge the two nodes. Let's say you can merge 1, 2 into the same subset. You can merge 1, 3 into the same subset, so that 1, 2, 3 are in the same subset already. Similarly, here in this example, so this one forms a circle. Before this edge 1, 4, before adding the edge 1, 4, 1, 2, 3, already 1, 2, 3, 4. Those 4 nodes already being union and they form the same cycle. And then when you are given this edge 1, 4, then you check their parents for the parent for node 4, the parent for node 1 in the unifying data structure, and then realize they have the same parent. They're in the same subset already. They have already been union. So you do not need to perform the union option for with this given edge 1, 4. So in that case, you know this 1, 4 is the output. So in this playlist, I have another video to cover the details of unifying the data structure. So basically how to implement the path compression, how to optimize the and the union by rank, and how to optimize the union rank from the basic implementation or from the naive implementation. So if you want to check the details for union find, please go find my video about the union find. Now I'm just going to first code up the unified data structure. So let's set a class union find, and then define initialization. So unified given n. So we have a parent, self.parent. So equals, let's use the default dictionary. And then self.rank equals the default dictionary as well. And then there are two functions. One is union, and then the other one is find. x1, x2. So before coding the union function, let's code the find function. So basically find function is given x, find its parent. So in that case, let's say if x is not equal to self.parent x, so let's use a result to separate this one. So if result is not equals to its parent, it means, okay, it's not the parents of this subset. So in that case, self.parent result equals self.parent result. So basically path compression. Self.result equals self, and then result equals self.parent result. So basically, this function, find function, is to given the x, we try to find its parent. If this x is not equal to its parent, which means, okay, we haven't found its parent yet. So in that case, we implement the path compression. So basically, assign the value of the grandparent to its parent, and then we use basically the way we are finding its parent is, okay, if the x is not itself's parent, which means we haven't reached the parent of this subset yet. So in that case, we just chase down the parent in order to find the parent of x. So again, if you want to learn about the details and why we implement it this way, please go check my video, the stand-alone video. You can find in this playlist. I have a video about the unifying data structure. So P1, P2 equals self.find x1, self.find x2. If okay, here I do now need the n from collection import default dictionary. So if P1 equals P2, it means, okay, S1 and S2 already unioned or merged before. So in that case, there is no need to perform the union. We just return false. Indicates, okay, they are. So, okay, more concise or process operation is already in the same subset. No need to union them. That's why we return false. So else we need to perform the union operation. If self.rank P1 greater than self.rank P2, in that case, self.parent P2 equals P1. So here we still need to have n. So the case is initially everybody's parents is itself. That's kind of initial states. So in that case, we do not need the default dictionary. So we just need I for I in range 1, n plus 1, n plus 1. So initially, everybody's parents is just itself. Similar for rank, I 1 I, and then initially everybody's rank is itself. Initially everybody's rank is 1. So because everybody is itself's parent, I in range 1 n plus 1. So here remember that this node is from 1 to n, denoted by 1 to n, instead of from 0 to n minus 1. That's why in the range it's from 1 to n. Okay, and then self.rank P2 self-rank P1 equals self.rank P2. So let's say if the rank of P1 is greater than the rank of P2, so in that case, P1 should be assigned as P2's parent. So that's why self.parent P2 equals P1. And then self.rank P1, we just increase it because P1 has already becomes P2's parent. So it should have the add the rank of P2 to P1 as well. Else, and then here, since we already successfully performed the union operation, so we just return true. So that is the class for union find. And then let's use that for solving our problem. UF equals union find n. So n equals the length of edges. So why we are getting n from the length of edges is because it's stated here as array edges of length n. And then we initialize the union find. And then for x1, x2 in edges, if union x1, x2 equals false, so in that case we return x1, x2. So after code the union operation, the function is relatively easy to solve. So basically, in this case, we just like try for every pair, every edge in this edges list. So we're just trying to perform the union operation. Let's say if the union operation returns false, which means x1 or x2 already in the same subset. In this case, if we add the edges x1 and x2, that would create a cycle. So in this case, we just return this edge. So this is the edge we need to remove. So let's run the code. Oh, union is not defined. So it should be unifind.union. Okay, so I get the wrong answer for this test case. Let me try to troubleshoot the problem. So there might be something wrong in my union find operation. So let me try to first take a look at this one. So it equals to n. And then when I initialize this one, the union find parent I equals itself. So basically the parent should be a dictionary. And then the key is 1 to n. And then the value is the same as the value of the key. And then the rank, initially everybody's rank is just 1. And then for the find operation, given the x, if x is not equals to its parent, then we know we need to chase down the parent. We use the path compression. I assign the grandparent to its parent. And then the result is self.parent result. So basically we are trying to find the parent. Okay, I think I made a mistake here. So it should be while. It should not end here. So this one will only end until I find the parents. Let me try submit one more time. Okay, so in this case it works. So previously I made a mistake. So the box I fixed is here. So in the unifying structure, I should continue run the recursion if I haven't find its parent yet. So previously I used if, so I only try once, but instead I should use while to keep trying to run the recursion until I find the parent. So this is the solution using the Unifying. So basically the key idea here is to first the Unifying data structure. This is pretty standard for any Unifying. So and then after we have this Unifying, then it's pretty easy. So we just try to check every edge in this edge list to see, okay, if we can if the node, if both nodes they already been in the same subset. In the same subset in this context means that, okay, there's a path that we can go from node x1 to node x2. Either they are directly connected before, or they can kind of connected via some other nodes. But we can reach x1 from x2, or we can reach x2 from x1. So in this case, if we add the edge x1, x2 in it, it will form a cycle. So that's why we want to output x1 and x2. So again, so if you want to learn about the details for the Unifying implementation, so please feel free to check my video on the Unifying. So you can find it in the same playlist of Unifying, or you can go to my YouTube channel and search for it. So in that video, I covered the details about Unifying operation data structure, basically how I arrive at the final implementation, and I also covered the path compression and the union by rank, the optimization for Unifying. So if you like my video, please feel free to subscribe to my YouTube channel. That would help a lot. Thank you.